the rest of today's lecture, I'd just like to present what are the most common experimental designs that you would find if you read today's fMRI literature. Not to say that there aren't additional very interesting designs, but these are probably the most common ones. The first type of design is known as a common baseline design. In this type of experiment, you would have two tasks, and you would compare each one to the same control or baseline task. In this cartoon example, you might have task A, which is viewing pictures of faces, as you see here. You might have task B, for example, viewing pictures of houses. And then you have one common baseline, one common control task, which probably would be something like scrambled images. So something where there is a visual stimulus, but there's no object in there. In fact, if you were sophisticated, you would take the very same images that you're showing in task A and in task B, and you would scramble all the pixels so that even though you have the exact same colors per pixel, you've scrambled them around, and so there's no face and there's no house in your baseline or control task stimuli. And now this, of course, allows you to detect what parts of the brain might be important for whatever are the processes underlying task A or task B, each one compared to baseline. So in my example, we'd be saying what parts of the brain respond to pictures of faces as opposed to scrambled images. And then the second comparison would be what parts of the brain respond to houses as compared to scrambled images. Now, this type of design assumes that the two experimental conditions, task A and task B, have similar psychometric property. So for example, there's an equal degree of activation across subjects, or the task difficulty is the same. And then you compare them to that same baseline task or control task. Now, two important issues that typically come up with this type of design. First, there are two ways of getting an activation when you compare some task to some baseline. For example, say that we did task A and compared that to the activations of control task or the baseline. Maybe if we do that difference, if we take that difference, we might see that some part of the brain is more, that some part of the brain, when you do that difference, turns out to be active. So the idea would be that in task A, that region of the brain was very active. In the control task, it was maybe either less active or it was at zero, compared to maybe just looking at the blank screen. And so when you compare the two, they give you a positive result. And this part of the brain is the part of the brain that really cares about faces. However, there's a second way of getting a positive value when you subtract two numbers that you have to be mindful of. And that is the case of a reverse subtraction. So in this scenario, pictures of faces does not activate this part of the brain. In fact, while you're looking at pictures of faces, this part of the brain is a little bit less active than if you were looking at nothing. Okay, the dashed line here is just looking at the blank screen. So when you look at pictures of faces, this part of the brain actually has an even smaller bold signal compared to whether you were looking at nothing. However, when you look at scrambled images, this part of the brain has an even smaller bold signal compared to looking at nothing, compared to sort of staring at the blank screen. So when you do this minus this, you still get a positive number. So when you get a significant difference between a task and a baseline, a task and a control task, you want to ensure that you're getting the difference because it's more active in one versus the other. and not just less D-active compared to the baseline. And these are known as reverse activations or reverse subtraction. Now, a second important problem that applies to this common baseline is also known as the IMAGER'S fallacy. And it goes as something like this. Maybe you have task A and control task, and then task B and the same control task. And maybe this is what you get. Task A, really you see activations compared to control here, and maybe a little bit here, and that's just about it. Task B, you get all these activations that you see here. And so you might be tempted, as somebody has done, to therefore conclude, and perhaps you're focusing on this part of the brain right here, you'll recognize that these two areas are the putamen and the caudate and are known as the striatum. And so you might be tempted to conclude that the striatum, just because you see a significant result when you do task B versus control, but you don't see a significant result when you do task A greater than control, you might be tempted to say striatum was more active in task B than it was in task A. Just because task B versus control gives you significant activation, but task A versus control does not, you might be tempted to say, well, therefore, during task B, it must be more active than in task A. However, that is not the case. This is what the IMAGER'S fallacy is. And in words, it would be that a difference in significance, meaning the fact that here it's significant and here is not, does not imply that there is a significant difference between B and A. Let me show you what I mean. So let's say that we were to look how active A is and how active B is, each compared to the control. Now, in this scenario, the intuitive answer is that during task A, you don't get much activation compared to control, which is sort of the zero line. Whereas during task B, you see all this activation, so it means that this part of the brain must be really active compared to whatever is the control baseline at 0. However, now this could be the case. However, it's also possible that while task B might have a big activation and a significant activation, task A might also have a big activation, just it's very variable. And so it doesn't give you a significant value when you do task versus control. So just because here you see a significant number and here you don't, does not mean that task B is greater than task A. Because what could be happening is that task B gives a strong response and it's not too variable, as you see shown here by the error bar. And so it gives you significant value when you do the test, the statistical test. Task A maybe also has on average a big response. It just varies a lot across individuals. And so when you do a t-test, for example, it says that it's non-significant. But of course, if you look at the average activation between task A and task B in this scenario, you would not want to say that this area was more active in task B than in task A. In other words, if you see that task B versus control gives you a significant result, and task A versus control doesn't give you a significant result, it could be that it's just that area is really active in task B, significantly so, and not active in task A. But it could also be that it's really active in both, just much more variable in one of the two. So just because you compare two tasks to the same baseline does not mean that you can make any inference about whether task A is greater than task B or vice versa. If you want to do that, you need to directly compare task A versus task B statistically. And that's where so-called parallel comparisons become important. Now, a parallel comparison is simply the direct comparison of task A versus task B and vice versa. So in this case, you would be comparing your experimental tasks one to the other. In our example, you'd be doing pictures of faces versus pictures of houses, and you'd be looking at what parts of the brain are more active during pictures of faces as compared to pictures of houses, which would be task A greater than task B. And then you'd also ask, and what parts of the brain are more active during pictures of houses, task B, compared to pictures of faces, task A. And this type of design, the parallel comparison of your two tasks, is usually an excellent complement to common baseline designs. So most often people use parallel and common baseline designs. So you compare two tasks of interest both to a common baseline, but then you also compare them against each other. Now this, of course, assumes that A and B still have similar psychometric properties, just like common baseline designs.